Hello, good afternoon, everybody. So today is the final lecture of the semester. So it is time to eat our cherry on the cake. It is time to consume the main product for which we were lecturing for basically 3 semesters. And this promised land is the a push out to pullback theorem for Leavitt path algebras. But let's start from the beginning. So we want to, in order to prove such a theorem, we will need some structural results for Z-graded ideals. I will in a second explain how we have grading for Leavitt path algebras. And in order to do it, we must have appropriate structural theorems, and I could find them only for Leavitt path algebras, and I didn't find them for cone path algebras. This is why we're going to bypass the cone path algebra step, unlike in the case of functoriality theorems. You remember that when proving both covariant and contravariant functoriality theorems, we are first proving it for cone path algebras, and then we said, all right, Leavitt path algebra is a quotient of the cone path algebra, so now let's make sure that under some additional conditions, the induced maps factor actually to the quotient. And that's how we proceeded. Here, well, in order to do such a thing, which is definitely desirable, I would need to know some structural theorems for cone path algebras, but I couldn't find them in this Leavitt book. Okay, so this is one thing to notice. Another one is that, and I'm going to recall appropriate results without proofs. Another thing I would like to emphasize is that we're going to postpone attacking the general problem, which could be phrased as follows. We could ask, what are the optimal properties of a commutative square diagram in this fancy category CRTB POG? So there's a CR condition, the target bijectivity condition, and properness condition. So what are the optimal properties of a commutative square diagram in this category, which is designed to induce homomorphisms of Leavitt path algebras, that guarantee that the contravariant Leavitt functor turns this diagram into a pullback diagram in the category of algebras and algebra homomorphisms. And let me explain why this is an interesting general problem, and why it wasn't such an interesting general problem when we're doing our push out to pullback theorem for Leavitt path algebras. And to this end, I suppose I have to use some more space. So let me stop sharing and use my whiteboard to explain what I mean. I start sharing again, this time with the whiteboard. Suck. Okay, as usual, it's not so simple. Okay, can you see my whiteboard?
Yes.
Yes.
Perfect. Okay, so you see, if I have a push-out diagram in some category, so I have, I don't know, A, B, C, D. Here I have some morphisms from D to B and from D to C. And then, well, I say that this is a push-out diagram in some category. Now I apply a contravariant functor, say F. I will end up with the following commutative diagram. Of course, it's a functor, so there's a commutative diagram to commutative diagram. It's contravariant, so I'm going to reverse the direction of arrows. And now it is a legitimate question to ask, well, under what circumstances a push out in this category implies that this is a pullback in this category. And under some reasonable assumptions, this should basically work. So push out should imply pullback. I mean, that's something that you would expect. However, by no means you should expect the opposite implication. So this implication, well, is to be expected under some circumstances at least. But the opposite implication, no, that's something you shouldn't think about, because this f can be a very stupid functor. It can be like the zero functor. I don't know. I can have say spaces on the left hand side. My category will be the category of spaces and maps on the left hand side, and the functor will just assign zero algebra to every object. So it will be in the category of algebras and algebra homomorphism, but it will assign zero to everything. Well, this is a functor. It surely will turn pushouts into pullbacks, but of course the opposite implication doesn't work. You see, the thing is that this functor might kill many things. In particular, it might happen that whatever prevents our diagram on the left-hand side from being a pushout diagram, this obstacle might be killed by F. So that when the image diagram under F will be a pullback diagram, despite the original diagram not being a pushout diagram. Okay, but there are some situations where it is really equivalent. And this is exactly what happens with sister algebras. So let's assume that we have a push-out diagram in the category of compact house of topological spaces. So our category is the category of compact Hausdorff spaces, and of course continuous maps. Then a commutative diagram in this category, of course, so let's put some notation. X, Y, Z, P, whatever. So here I have some continuous maps FG. Here I have some other maps. I don't know, maybe capital F and capital G. So such a commutative diagram in this category is a push-out diagram if and only if the induced diagram of unital sister algebras is a pullback diagram. And this induced diagram is, of course, take all continuous functions on P, then you take the pullback of the continuous map F, that's a star homomorphism into the unital sister algebra C of X. Likewise on the other side, G star, C of Z, lowercase f star to C of Y, and lowercase g star from C of Z to C of Y. Okay, and so in other words, what you can say is that you basically have that C of a push out, so X, Y, Z is just the same as the pullback of C of X, C of Y over C of Z. Okay. You have this fundamental equality, and what is important is if and only if. So if you have a sister algebra of that sort, then you know that this is the sister algebra of a push-up. Okay, and this is something which might hold to some extent, at least. I'm sorry, I didn't check it. If you look at the category of spaces with proper maps, category of sets with proper maps, and your functor, instead of this Gelfand functor assigning to your comparison topological space the unital sister algebra of all complex value continuous functions, will be just the functor which assigns to a space for any to a set X and any field K all finitely supported maps from X to K. I didn't quite verify it. Perhaps it works at least for finite sets. But here you would expect a similar kind of exactness. So this is a functor which should not kill too much. It should remember. It should be somehow faithful. Okay, in some way. So that's why when we are looking at path algebras, and remember that after all, what is a path algebra? A path algebra of a graph E is nothing but finitely supported maps on the space of all paths in E into our ground field K. All right. So this is exactly this kind of a functor I just discussed for any sets. Okay, this is a nice contravariant functor which should be reasonably faithful. So that's why we, without any ado, we from the start we're saying, all right, I need to have such push-out diagram of graphs so that the induced diagram between spaces of all finite paths is also a push-out diagram. Okay, and this turned out to produce a lot of conditions. Okay, just to induce a homomorphism of path algebras, all that were required was that we really have a graph homomorphism, not a path homomorphism of graphs, but a path homomorphism, and that this is a proper path homomorphism, a homomorphism of graphs, and that was enough. But so these were pretty mild conditions, but then really to ensure that we can say that taking the space of all finite paths in the push-out graph E of G is the same as the push-out of these sets. Now that's a tough book, and this was a lot of work, and it brought about lots of additional conditions. Okay, but here this was reasonable to expect it, because if this contravariant functor behaves similarly to the Gelfand functor, then, well, I mean, there is not very much hope in something natural or interesting to occur if what you start from, the diagram you start from, is not the push-up diagram. Okay, so that's why we proceeded this way. But here, when you take the Levitt functor, so you're not just using this functor. You take this algebra and then you quotient it by quite a substantial idea. Okay, so you kill a lot of things. So it's very reasonable to assume, and in fact, I'm pretty certain it's true, that you might construct some diagrams which are not push-out diagrams, but after application of the Levitt functor, so the contravariant Levitt functor, so the functor which assigns to your graph a Levitt path algebra, and on morphisms it acts in the contravariant way. That this would be still a pullback diagram. So this is an interesting question to ask in general, but it's also very difficult one. Okay, and instead I want to prove a much simpler push-out to pullback theorem. Let me now go back to my lecture notes. So I start sharing again, and now not the whiteboard, but the notes. Okay, and I should have somewhere a highlighter. This is eraser. Yeah, let me highlight. So this is what we just discussed. And this is a general, difficult general problem. You might do your PhD on this if you want. What I'm going to do instead is to see what happens if I look at the push-out to pullback theorem for Levitt-Pav algebras and try to combine it with the requirements of this category, which is designed to admit the contravariant Levitt function. So in other words, I'm trying to do the following thing. Okay, I have a nice pullback diagram for Levitt-Pav algebras. Okay, so I have K of E, KG, KF. I have a nice pullback diagram here. KE, KF, and here KG. And I'll try to see if somehow this pullback diagram can be factored, can descend to a pullback diagram for Levitt-Pav algebras. But then, for starters, I need to upgrade this push-out to pullback theorem for Pav algebras of graphs to Pav algebras of extended graphs. Okay, because Levitt-Pav algebra is not a quotient of a Pav algebra of the Pav algebra of a graph. It's a quotient of the Pav algebra of an extended graph. So first, I need to be able to have a theorem where these graphs are replaced by extended graphs, and see what conditions we have then. Okay. But before we do it, we need to look at a very simple, trivial proposition, if you want. It's now in the category of maps and sets. So I have two push-out diagrams in the category of maps and sets. Okay, nothing fancy. It's as simple as it can be. I have one with indexed with ones everywhere and one with indexed with two everywhere. So these are two completely independent push-out diagrams. And I claim the following. I claim that now if I take the disjoint union of x1 and x2, y1 and y2, z1 and z2, and the disjoint union of the maps f1 and f2 and g1 and g2, and then I fancy to have a push-out, to have a push-out in the category of sets and maps of these two maps, that whatever I will obtain will be the disjoint union of push-outs. So in other words, what I'm saying is that the push-out of a disjoint union is the disjoint union of push-outs. This is a certain commutation. And this is a completely trivial proposition, and I'm pretty certain that it follows from some very categorical mumbo jumbo, some highbrow abstract nonsense, because it's a certain commutation of combining push-outs. I mean, the disjoint union is also kind of a push-out. So I'm sort of iterating push-out, and I'm saying that they commute under certain circumstances. But here, all these fancy possibilities notwithstanding, you can simply check it by verifying the universal property. If you write here an arbitrary space omega, and you assume that you have maps rendering the diagram commutative, okay, then you can basically prove using the universal property for the push-out number 1 and push-out number 2, you can prove that when there exists a unique map here rendering these two triangles commutative, which proves when this is a push-out. Okay, and now it has a very nice, let me erase it. It has a very nice and useful corollary. Namely, I know how this extension functor behaves with respect to push-outs. So now let EGF be a push-out of graphs, any push-out of graphs. Then the extension of a push-out graph is the same as a push-out of the extended graphs. Okay, I hope it is obvious. I think it was Niklas who was proving that if we simply define the push-out graph as the push out of vertices and the push out of edges with the appropriate induced maps, then indeed this is a categorical push out in the category of graphs and graph homomorphisms. Okay, so it might as well take this explicit construction. And then when you look at it like this, well, vertices in the extended graph and in the graph itself are exactly the same. So the first component is identical, nothing changes. And when you look at the second component, this is precisely this kind of a proposition that we have above, okay? Because if you look at, so I'm saying that it suffices to look just at the edges, and when I write this equality for the edges, I'm looking at the following. I'm looking at E1 disjoint union G1 F1 extension on one hand side, and this should be equal to E1 disjoint union with E1 star. Okay, so that's one piece. Now I take the push out of a G1 bar, but G1 bar is nothing but G1 disjoint union G1 star. And here I have F1 disjoint union F1 star. So basically what I have on the right hand side is nothing but the push out of disjoint unions, okay, and what I have on the left hand side is what I have over here, the disjoint union of push outs. So this is the disjoint union of push outs, and I'm saying that by trivial verification, this is the same as the push out of the disjoint unions, which is what you have over here, okay. So this way you can conclude this corollary, which is very useful. And now with this corollary at hand, we can upgrade the push-outs to pullback theorem for Levitt-Pav algebras of graphs to the Levitt-Pav algebras of extended graphs. Let me erase my reasoning here so that it doesn't distract anybody. And now I'll explain how these lemmas and how lemma 2.42 and theorem 228 come into play. So theorem 228 is precisely the theorem, this push out to pullback theorem for Levitt-Pav algebras, okay? Oh, come on, erase yourself. Why is it so complicated? Begun, okay. Never mind the dots. So our preamble is that we have a push-out diagram in the category of graphs and proper graph homomorphisms. So using this lemma 242, we know that if we apply this extension functor to proper graph homomorphism, we'll get proper graph homomorphisms. Okay. So what are we doing here? We put bars everywhere. And the induced the bar maps are now also proper graph homomorphisms. Okay, so we have a desired diagram, the properties, and then by this corollary above, we can now rewrite it as E bar disjoint union. Sorry, the push out over G bar with F bar. Okay. So basically, we have the same diagram as before with the same properties, but now for the extended graphs. Okay, and we have it due to corollary 2.52 and lemma 2.42. All right, so that's like the first part. But now we have some assumptions. So first, let's look at the assumptions 1 and 3. Well, F0 and G0 are the same for graphs as for extended graphs. Okay, So then, of course, injectivity for graphs is equivalent to the injectivity for extended graphs. Very much in the same way, injectivity on edges is tantamount to the injectivity of edges for extended graphs. That's very easy to understand, because if I look at a map, say F1 bar from E1 bar to say F1 bar, then I have to remember that this is just the disjoint union of E1 disjoint E1 star, likewise F1 bar, and that this okay, so I should write it here, equals to F1 disjoint union F1 star. And this map F1 basically is also the disjoint union of maps. This is F1 on the first component, disjoint union with F1 star on the second component, and this F1 star basically means that I take the starred edge, I de-star it, I apply F1, and then I star the image. So that's you know, it's clear that I cannot glue any star edges with non-star edges, and there, because non-star edges go to non-star edges and star edges go to star edges, when the only possibility of having failure of injectivity is to glue non-star edges with non-star edges and star edges with star edges. But doing so would require that F1 is no longer injective, or that F1 star is no longer injective. But this F1 star is, of course, just a copy of F1. So these are basically identical maps, just on copies of sets. So failure of injectivity here would imply failure of injectivity there. Okay, and the other way around, of course, is also obvious. If you are injective here for the extended graph, then of course you're also injective for the graphs itself, because a component of an injection must be an injection. Okay, so that's if and only if. All right. So conditions 1 and 3 are very easy to grasp. Again, I'll struggle with erasing stuff. I don't know. I just don't know how to make it faster. Sorry about this. Oh, I should have left these bars in the diagram, but never mind. And now let me scroll to this theorem 2.28. Okay, it shouldn't be too far behind. Well, maybe I'll make it a bit faster. Yeah, it was the previous semester, so sorry, yes. Yes. So it's a bit further up. To 28. We're almost there. Here you are. Okay, so you see the assumptions 1 and 3 are the same, but now if you look at assumption number 2, there's one color condition. It just tells you that if you have two edges with a property that when one edge ends, another edge begins, okay, so this is X and this is Y. If such a thing happen, then X and Y must be in the same subgraph. So they are either simultaneously in E1 or they are simultaneously in F1, okay? And this is, it's called one color condition, because if you think about edges from one graph as being one color and edges from another graph being another color, then what we are saying is that they cannot be of different colors. Of course, here there's a slight subtlety because you might have plenty of edges which are in both graphs. Okay, so I'm not saying that x, if x is in E1, then y cannot be in F1. Of course, it can be in F1, but it must also be in E1, unless x is also in F1. Okay, so that's the thing. However, that's for graphs. So when you add these ghost edges, the edges going in the opposite direction, well, then when you look at x and y, you might have that y is a starred edge. So if a starred edge begins where the other edge ends, then it means that actually the y edge ends where x ends. And you have all possibilities, because you can have that x is starred and y is not starred, you can have that both are starred. So in other words, you must consider all four possibilities. You have a path like this, you have a path like that, endpoints meet or start points meet. Okay. For any of these situations, when you star appropriately any of these components, any of these edges, well, you'll get exactly this condition. Okay. So this means that we must demand a little bit more for graphs in order to have such one color condition for the extended graphs. Okay. And this is why I reformulated this condition in the following way. Now scrolling back again is a bit of a hassle. And that's the drawback of using Drawbird PDF. It's a little bit sluggish. But then it's so convenient to write on your slides. Oh, come on. I'm trying to scroll by using a strip on the right, so it should be fast. But because it's an online service, it has its delay. Oh, we're almost there. Okay. So you see, this is why I reformulated this one color condition into this one. So basically what we're demanding now is that if I take endpoints of one edge and endpoints of the other edge, if these two sets intersect non-trivially, so they have at least one vertex in common, then you must have that both of these edges are simultaneously in E1 or they're simultaneously in F1, okay? Under this condition for graphs, you have the previous one color condition for the extended graphs, okay? So now when you combine everything we said so far, now we can conclude, like in this theorem 2.28, that indeed, when you take the Leavitt-Pav algebra of a push out of extended graphs, this is nothing but the pullback of Pav algebras of extended graphs. So that's this key formula, which we now have for the extended graphs. And of course, when I look at the commutative diagram, the induced commutative diagram, it is a pullback diagram, okay? So everything as we had before, without talking about extended graphs, but now for extended graphs. And we could do it because we upgraded our assumptions on the push out of graphs so that it yields an appropriate push out of extended graphs. And then since theorem 2.28 was true for absolutely any graphs and graph homomorphisms, proper graph homomorphisms, then of course we might as well have extended graphs and extended proper graph homomorphisms. Okay, so this corollary is done. Let me not dwell upon it anymore. And let's continue. So now our strategy is to combine the assumptions of corollary 2.53 with the assumptions of for the contravariant functorial theorem 250 for Leavitt-Pav algebra. And that's exactly the conditions of this category C, R, T, B, P, O, G. Okay, because on one hand side, we want to have this pullback diagram. Okay. On the other hand, we hope that, all right, if we have some further assumptions such that this commutative diagram induces a quotient commutative diagram, where now instead of path algebras, I put Leavitt path algebras. Okay, so LKG, LKE, pullback over LKG, LKF, and here LKE, here LKF, okay. So basically what I'm doing, I'm saying, all right, now under these additional assumptions of C, R, T, B, P, O, G, I know that all these arrows descend to quotients, and these quotients are Leavitt path algebras, okay? And now I'm wondering what conditions are sufficient so that the thus induced commutative diagram, because no doubt then I do obtain a commutative diagram for Leavitt path algebras, okay? But is it a pullback? This is the question. Is it really a pullback diagram? Okay. So well, actually, what I wrote here was wait a second. That's not what I meant. This would be a tautology. So here's the result. Okay. What I must put in here is Leavitt path algebra of the push-out graph. So EGF. Okay. Right. Because here I have nothing but the path algebra of the push-out graph. It's a result that I can replace it by the pullback. Okay. So that's the hope. That's our line of reasoning. That's something much simpler than trying to attack this general question of what are the optimal conditions for a push-out diagram actually for a diagram. Doesn't have to be in a push-out diagram. What are the optimal conditions for a diagram in the category of proper graph homomorphisms, so that the induced square not only is a commuted diagram, but actually a pullback diagram, right? That's a very difficult general question. Okay. Okay. So instead, what we are going to do, we're going to combine this assumption, and here something actually quite interesting happens. So first, as you might remember, I explained it, I think, a week ago, that the target bijectivity condition, which is required for theorem 250 for this Leavitt path algebra theorem for functoriality of the contravariant Leavitt construction, that this target bijectivity condition combined with vertex injectivity conditions imply that we have to work with injective graph homomorphisms. So the only push-outs of graphs we can consider are actually unions of graphs. Because they are injective everywhere without the loss of generality, you might as well assume that instead of injections, we are working with inclusions. Because the image graph is isomorphic with a graph. Once your morphism are injected. So that's just a hassle with additional notation. So you might as well consider the unions of graphs instead of general push-outs. Okay, and maybe I will go back to this reasoning to remind you. It was an elementary fact proved somewhere there. See, this is this number 2. Okay, so if I have an injective graph homomorphism, so if I have a graph homomorphism that is injective on vertices and satisfies the target bijectivity condition, and such that the target bijectivity condition is injective. Yes, exactly. A graph homomorphism that is injective on vertices satisfies the target bijectivity condition is injective. Okay, so it's also injected on edges, right? So we end up basically with talking about subgraphs. So here was a simple argument. And that's a big deal because somehow you see that already at the first sight, when you want to combine this CRTB-POG with assumptions for our contravariant functionality theorem for Levi-Popov algebras, well, you end up with something very restrictive or still very interesting, namely the only push-outs you can work with are simply unions of graphs. Okay, this makes your life simpler, but now I somehow want to argue what kind of unions of graphs you have to think about. Okay, so now assume that F and G is the union of graphs F and G. Remember that the union of graphs not always exists, right? The union exists if and only the intersection exists, and the intersection exists if and only if intersecting the sets of edges, you get a subset of edges on which two target maps agree. Okay, that's necessary for the intersection to exist. And if intersection exists, then the union exists. Okay. And now we assume that both these inclusions, we think about the inclusions as injective maps, but there are elements, that there are morphisms in our specifically designed category, CRTB-POG. Okay, so that we are guaranteed that there exists the induced homomorphisms from LKF to LKF intersect G, and from LKG to LKF intersect G. Okay, and what I'd like to use now, I'd like to establish their subjectivity. I simply wanted to say is that, all right, the first naive combination of assumptions immediately brought us into the realm of unions of graphs. And now I want to show you that once we in the realm of union of graphs, in fact, you can deduce that you must have these admissibility conditions that we talked about in the previous semester. So that's quite beautiful, because you see that these admissibility conditions are basically forced on you, but at least when you restrict yourself to the unions of graphs, not to arbitrary push-outs, and that's what you need to do if you follow this naive path which I outlined, this simpler, this ansatz path that I outlined, then admissibility is not an option, it's not a choice, it's something that you really need to have. And let me argue why. I find this argument quite interesting, and it's based on a beautiful theorem from the Levi-Popov algebra book. Okay, but